Welcome. In today's video, we are going to derive the mean and variance of the binomial distribution. We are going to do this in two ways. The first way, using the typical definition of the expected value of a random variable and the variance, and using the PMF and sticking those together and deriving it using a more algebraic way. The second method is we're going to consider a binomial distribution as the sum of independent Bernoulli distributions. For now, let's have a look at the first way. So recall if x has a binomial distribution, or I should do it in the full writing, binomial with parameters n and p, where n is the number of trials and p is the probability of success of any one of those trials, then the PMF, or the probability mass function of x, is given by the following. So we can write px of x, or the probability that x is equal to the observation x, is equal to n, choose x, p to the power of x, 1 minus p to the power of n minus x. So, using the definition of the expected or the expectation of a discrete random variable, we can say that is the sum across all values of x in the support of x times the probability mass function. Now we know our PMF function here is obviously only defined for x values 0, 1, all the way up to n, and so our terminals of our summation simply go from x equals 0 to n. We still have our x, and then we multiply by the probability mass function, which we just had up there, p to the x, 1 minus p to the n minus x. Here is where it can become interesting. The first thing to note is that the first part of the terminal, the x equals 0, when you plug in x equals 0 into this expression, you actually get a 0 out the front. And so the whole first term in this summation is just 0. So I'm going to just simplify it a bit and instead say it's just equal from x equals 1 to n of x times yada yada yada. One of the other things that I'm going to talk about is I'm just going to expand the combinatorial factor here, and quite simply n choose x is by definition n factorial over x factorial over n minus x factorial by definition. And of course we've still got the p to the x, 1 minus p to the n minus x. The next part is, of course, to recognize that the x in this expression here can actually cancel out with the x factorial. So in this particular instance, we can still write the summation x equals 1 to n. We've still got the n factorial, but if you recall, just as a side little piece, x factorial can be written as x times x minus 1 factorial. And so technically the x here in the numerator, or the x out here at the front, can cancel with the first x here in the denominator, or the denominator here, leaving us with the x minus 1. So that's what we're going to do here. And I haven't given myself enough space, or no, I have given myself enough space. So you got n factorial over x minus 1 factorial, n minus x factorial close the bracket, p x 1 minus p n minus x. So far, everything seems pretty good. We're going to do one last sort of sneaky, I would say, substitution here. So what I'm going to do is I'm going to define the variable, and the reason I'm defining the variable here, if you see my x minus 1, I'm going to define the variable y is equal to x minus 1, just as a form of substitution. So there's a few things that have to change here. One, that means wherever I see an x, that has to be equal to y plus 1, pretty straightforward. And wherever, that's one thing that has to change in this expression. The other thing that needs to change in this expression, of course, is the terminals. Because if we're going from x equals 1 to n, that is the equivalent, actually, if we think about it, when x is equal to 1, y is equal to 0, and when x is equal to n, y is equal to n minus 1. So now we can put in our substituted values, y factorial, n minus, now I'm going to be careful here, y plus 1 in brackets factorial, back there, p to the y plus 1, 1 minus p to the n minus, n minus, and then again, y plus 1 here. Now, what are we going to do here? Well, again, I'm going to be a little bit tricky now. My aim here is actually to make the expression inside the summation look more and more like a PMF we're familiar with. I'm going to try and manipulate it in a way so that it looks like a probability mass function of another binomial random variable. So the first thing I notice is, if you remember or you recall going back up to the definition of our original probability mass function, where we had n factorial over x factorial and n minus x factorial and, p to the x and 1 minus p to the n minus x. You can see here a p to the x. There's sort of something equivalent here of a p to the y, but we've still got this plus 1 out the front. So what I'm going to do there, for example, is I'm going to take a p out the front of the expression to leave me with p to the y. Now, we've got our x factorial here is our x factorial here. That seems okay. This is a bit of a problem statement as well, and it's a bit of a challenge to try and maneuver, except if we do something like this. And this is where the genius of it all is. The other, and this is the kind of the hint, by the way. You can see here the original terminal up here was n. Now the terminal has become n minus 1. So now maybe if we try and stick n minus 1 somewhere in here, we're going to get our expression. So the n factorial, if you think about this, can be written as n times n minus 1 factorial. And you might look like we're going backwards, but I promise you we're not. Y factorial, Now, if you have a look here, you've got n minus y and then the n minus the plus 1. I'm going to rewrite that as n minus 1 minus y factorial. That's a nice expression there. Times, again, p to the y plus 1. We're going to take one of the p's out, and we're going to be left with p to the y. And again, we're going to rewrite this expression at the back as n minus 1 minus y. So 1 minus p, n minus 1 minus y. So now we can do a bit more algebraic manipulation. One of the things that we're actually going to do here is, the first thing we're going to do is, you've got a p and we've got an n. We're going to take those all the way out the front. So we've got np. You've got y equals 0 to n minus 1 of n minus 1 factorial over y factorial, again, n minus 1 minus y factorial, all good, p to the y, 1 minus p to the n minus 1 minus y. Bit challenging, but I promise you we're only a few steps away, because what we're going to do next is I'm just going to label this n star, or I'm going to label as a new n star, is equal to n minus 1. And by doing that, what we get in the bottom part, or the next step, is np y equals 0. Now, n minus 1 is just n star. N minus 1 is just n star factorial. Y factorial stays the same. You've got n minus 1 becomes n star minus y factorial. Then you've got p to the y, and then 1 minus p to the n star minus y. And what do you notice? After all of that nice, long working, this is the PMF of a binomial distribution with parameters n star and p, if you recognize this expression here. And not only is that the case, we're actually summing the PMF function from all the possible values of that binomial distribution from 0 to n star. And what do we know about when we sum the PMF across all of its possible support? That, by definition, is equal to 1. And so we can actually just write is equal to np times 1, which is equal to np. And there you have it. We have an expression for the expected value of a binomial distribution. We are now going to attempt to derive the variance of the binomial distribution using a similar technique. Now, one of the things that typically, if you recall, to find the variance, you first need to find the expected value of the second moment, or the expected value of x squared. The difference being, in this particular instance, we're actually going to use a bit of a trick. And we're going to express the variance, the second moment in a particular expression. So let me first show you the expression and give you comfort that that particular expression is in fact the second value, or the second moment, plus e to the x. So this is the expression we're going to use. In fact, we're just going to evaluate this part of the expression because we know this part of the expression. But I'm going to assure you that this is in fact equal to the second moment. And the way I can do that is first by expanding the brackets in the first term. So that would become x squared minus x plus e expected value of x. Then because of the properties of expectation, the expectation of a sum, or there in fact the expectation of the subtraction of two terms, you can think of as the expectation of the first term minus the expectation of the second term. And then of course we've still got the plus e to the x at the end, and surprise, surprise, the minus e to the x and the plus e of x, expected value of x cancel. And so we are in fact left with this expression as x squared. And we're going to use this property to our advantage. And the reason we're going to use this to our advantage is because this expression here is actually much easier to evaluate, believe it or not, than simply just evaluating this using the PMF. And so, without further ado, let's have a look at how we can do that. So, the expected value of x minus 1 is equal to, well, by definition of expectation, that is the sum of x on its support of the function inside the expectation, so x minus 1 times the probability mass function of x. Then, of course, the next step is to substitute in some terminals. Again, remember, x goes from 0 to n, and we've got x minus 1 times n, choose x, p to the power of x, 1 minus p to the n minus x. Again, we're going to expand this notation. However, the first thing before we do expand the combinatorial factor here is to again similarly recognize that for x equals 0, this expression out the front collapses to 0. And in fact, for x equals 1 as well, this expression also goes to 0. So what does that mean? It means from x equals 1 and x equals 0, this whole expression goes to 0. And so what we're going to do is in the next step here, I'm going to ignore the first two factors and I'm going to say from x equals 2 to n of x minus 1, and then of course expand the combinatorial factor. You get n x factorial n minus x factorial here. And of course, p to the x, 1 minus p to the n minus x. So, once we've done that, we're going to use a very similar technique. And the technique is going to be something like this. I'm going to allow two things. The first sort of substitution I'm going to make is I'm going to say, well, actually, before I do that, x factorial, as we discussed, could be written as x times x minus 1 factorial. And in fact, that can be written as x minus 1, x minus 2 factorial. So we're going to use this expression down here, and then you'll notice that in this expression here, the x and the x minus 1 will cancel with the x minus 1 here. So in the numerator, what we're going to be left with is just the x minus 2 factorial. And I've accidentally moved that too far. So let's go now to the next step. Again, sum x equals 2 to n of n over x minus 2 factorial, n minus x factorial, nicely put like that. We've got the factorial signs at the top. P to the x, 1 minus p to the n minus x. Again, we're going to make a smart substitution here. And the smart substitution is going to be the fact that this x minus 2 we're going to label as our y. So that becomes x minus 2. This gives our next part of the expression. Goes from x equals 2 to, apologies, now we've got to change the terminals, of course. So if we're going from x equals 2, and also rewriting this as the fact that we can write x is equal to y plus 2. So when x equals 2, y is equal to 0, and when x equals n, y is equal to n minus 2. So our terminals here become y equals 0 to n minus 2. We've still got our n factorial expression. We're now going to replace x minus 2 with y. We've got n minus here y plus 2. In our factorial expression, we've got p to the y plus 2. And again, we've got y minus p to the n minus y plus 2. Now, I'm going to just pause there for a second. And in a similar fashion to the way we did it before, we're going to rewrite this a little bit. We're going to rewrite this as the sum of y equals 0 to n minus 2. The n factorial we can rewrite as n minus 1, n minus 2 factorial. And we will explain why that is the case. We've written it like that. We've got y factorial here. We're going to rearrange this expression here so that it in fact now becomes n minus 2 minus y factorial. So you can see we're doing a very similar technique. We're trying to make this look like a PMF of a binomial distribution again. This p to the y plus 2, we're going to rewrite as p squared times p to the y. And then this expression at the back here, we're going to still have the 1 minus p, but now we're going to rewrite this as n minus 2 minus y. And now we're going to make this very important n star substitution, which is going to be n minus 2. So we're going to say n star is n minus 2. So wherever we see n minus 2's, we're going to substitute with n star. The first place we see n minus 2 is in fact in this expression here, which is the n minus 2, so n star. I'm going to leave the n and the n minus 1 here, n minus 1, but then the n minus 2 factorial becomes n star factorial. Put in the denominator y factorial, then n star minus y factorial. Still got our p squared, still got our p to the y, and we still have our 1 minus p, but now it is to the n star minus y at the front. Now, the n minus 1 and the p squared are all independent of the terminal, which is, or the terminal index, I should say, the y. So we can bring those out the front of the summation. So this, of course, leaves us with n minus 1 p squared out the front, sum of y equals 0 to n star of n star factorial over y factorial n star minus y factorial p to the y 1 minus p to the n star minus y. And again, we have now discovered a very similar result here, where our binomial expression, or the expression inside the summation, looks very similar to the PMF of a binomial. In fact, it is the PMF of a binomial, with n star as your number of trials, p is your probability of success. We are summing across all the possible values of that distribution. So going from 0 all the way to n star. And so we know this whole expression here collapses to just 1 by definition of a PMF. It has to sum to 1. And therefore, we can write this as n minus 1 p squared. And using that technique, we can now find the expected value of x squared. So again, using the expression we had before, the expected value of x squared was the expected value of x minus 1 plus expected value of x, which in this case is n minus 1 p squared from above, plus the expected value of x was np. And finally, after all of that algebraic manipulation, we can come up with the variance of x, and the variance of x, by definition, is the expected value of x squared minus the expected value of x all squared, which is now going to substitute in our expression n minus 1 p squared plus np, that's the first part of the expression that we had, minus expected value of x all squared, that is minus np all squared. To get there, what we're going to do is we're going to expand everything. So the first part is expanding this this expression here. You got n times p squared. That gives you n squared p squared. Then you have your n times negative 1 times p squared, which gives you your minus np squared. Then you've got plus np minus n squared p squared from the bottom, or from the second part of the expression. This n squared p squared cancels with this n squared p squared, which leaves us simply with np minus np squared. We can factor out the np, and so we get np1 minus p. And this, ladies and gentlemen, is the formula for the variance of a binomial distribution. And of course, if we want to go one step further, to complete all our bases, to cover all our bases, the standard deviation of x, which is by definition the square root of the variance, is simply equal to the square root of np1 minus p, the expression that we just derived. Now, that, if we go through, is quite a lot of manipulation here. And what I will do for benefit is this is where the variance part begins. fact, it's actually a little bit higher. All good. Let's just continue onwards. Now, this was a lot of expression, a lot of algebra, and some really good algebra, by the way. This technique is very common when dealing with discrete random variables in particular, where we are sort of inserting, or we're using the definition of the a discrete random variable expectation and variance, and we are manipulating algebraically the expression so that the expression inside the summation looks like another PMF. Common technique. That being said, there is actually a far simpler way to get to the result. The simpler way is actually recognizing one of the definitions of what a Bernoulli distribution is. So we've seen that, x is distributed binomial. Binomial means that NP means you've got this very frustrating PMF. Not frustrating, let's say, but complex to manipulate PMF. Right? But there's another way we can consider the binomial distribution, and that is this way. And we can write x as the sum of several random variables, xn, or in shorthand form, I equals 1 to n of xi, where each of these random variables, right, so x1, x2, xn, where x1, x2, xn, they are all independently and identically distributed with a Bernoulli distribution. This is, of course, with parameter p, the same parameter p. This is, of course, by very definition, what a binomial distribution is. In each point in time, you are conducting a Bernoulli distribution, which could either take 1 or 0, and in each particular instance, whether it takes 1 or 0, it has probability p, and then the total number of successes within that particular binomial distribution you can think as the sum of the Bernoulli distributions. Because, for example, if you get 1 here and a 0 for the second observation, then overall in the first two observations, that's 1 out of 2. That is the equivalent of having 2 trials and only getting one of them. Or you get 2 trials, both successful, you get 2 out of 2. This way of expressing the binomial distribution will allow us to quickly get to the mean and variance. And I'll show you that in a sec. So, using this method, we're going to have the expected value of x is equal to the expected value of x1 plus x2 plus ... plus xn. Now, using expectation, or our rules of expectation, the expected value of a sum is in fact equal to the sum of all the expected values, x2 plus ... plus expected value of xn. Now, going back to another video that I would have done where we derived the expected value of a Bernoulli distribution, we know that a Bernoulli distribution has the following properties, in fact. It has an expected value of p, and it has a variance of p 1 minus p. So if we're taking the expected value of the first one, the expected value of the second one, the expected value of the nth term, they're all the same. So they're going to be p plus dot 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 plus p. And how many times are we summing up the p's? Well, that's n times, because there are n particular trials. And so we now can rewrite this as simply np. And look at that. We have saved ourselves a whole page of working that we had originally up the top, just using our understanding of the binomial distribution. We can do something similarly for the variance. So the variance of x is equal to the variance, again, of the sum x1 plus x2 plus dot 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 plus xn. Now, because they are independently and identically distributed, the variance of a sum of independent variables is in fact equal to the sum of the variances. This is only true for independent random variables. x2 plus dot 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 plus variance. And of course we know they are independent because the whole point is that one trial, the first trial, doesn't affect the second trial, which doesn't affect the third. Now again, the variance of x1, they are all the same variance. They all have the same variance of p1 minus p that I took above, plus p1 minus p, plus dot dot dot, plus all the way to p1 minus p. And of course, again, we're deriving that n times, or we're summing that n times. And that finally gives us a value of np1 minus p n times. And that is a simpler way to get to the mean and variance of the binomial distribution. I hope that video was informative. I hope to see you in the next one. Thanks for watching.